Hello, fellow problem solvers. So today we're going to be doing a problem in polynomials. I invite you to try this problem out for a minimum of 10 minutes, ideally 30 to 45, not more than an hour and a half. It's a pretty cool problem. There's two types of solutions, and I'm going to show both of them to you. So p of x is a polynomial of degree n, such that for i's 0 through n, p of I is 2 to the power of I. Determine p of n plus 1. Right? So there is the technical way saying that if I have n plus 1 points defined in a polynomial, that uniquely defines a polynomial. And one way to go about proving this is to say if p of x, say we have values p of x1, p of x0, p of xn, and these are equal to yn, y1, y0, p of xi is equal to yi. And how we construct this polynomial is that we can construct it as a p of x as a sum of polynomials, call them q of x, q1 of x, actually q0 of x plus q1 of x plus qn of x, this one times y0, this one times y1 times yn, such that qi of x is equal to 1 for x equals xi, and is equal to 0 for x equals to x, actually for xi specifically, and for xj not equal to xi, it's equal to 0. Right? And I'm assuming these are different values, right? So how can we construct these polynomials? Right? And why does this work? Because if, say, we put in xi, then every single one of these except xi will be 0. qi of x will have a yi next to it. That will be 1. This will be 0, and everything else is 0. And for that one, we will be able to finish it up. Why is this cool? Why do it like this? Because you have a lot of zeros. You have n minus 1 zeros. And that tells you because all these q's are also degree n. And you've just given them n zeros. Now you know that every qi of x is going to be the product x minus xj, for j is equal to 1 tail n, and then you're just going to like forget about x minus xi, right? That's what every single one of these is equal. So the x minus xi is canceled out. And then you need to just make sure that once you actually plug in x minus xi in every single one of these, that you will be able to get a 1. So actually to write this down more neatly, for j is equal to 1 and j is not equal to I. And then all of this is going to have to go over the value once I put in x equals xi, which is going to be the product xi minus xj, for again, j is equal 1 through n, and j isn't equal to I. And then this thing right here is a constant thing. This is a polynomial, so we're done. Like we've sort of said, now we know how these things look in general, and then we can just apply this formula to our polynomial and really be done with it, right? Another way is like you can play with smaller cases and then figure out, oh, this is following this formula, and it's all nice and good. This is a very technical approach, right? This is when you know a lot of stuff about polynomial and you just like go, 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 and go, and you finish up. You will not see it, I doubt, let me put it, I doubt, so that I can hedge my bets here. I doubt that a problem like this will come up at the IMO where you can just solve it by pure computation. And if it comes, it's going to be a 1 or a 4, not a 2 or a 5, probably. Though you can't predict how that will turn out in the future. Because like IMO 2020 problem 2, come on. It's pure computation. It's like theory and computation, but that's a rant for another day. So we know how p of x looks, and now we can see, okay, p of I, p of For I equals 0 through n, we have p of I, and then we can construct p of x. Actually, let's see what p of x ends up being. P of x ends up being so y0 through y10 is going to be a sum. So the yi are going to be 2 to the power of I from I equals 0 till n. And then these qi's are going to be, so it's going to be times x minus, so what are we going to have? We're going to have, so say for the value, which value should I pick? So for I equals 0, I'm going to have from, actually this is from j is equal to 0, from j is equal to 0 here. So what am I going to have for the 0? I'm going to have 1 minus 0, 2 minus 0, 3 minus 0. I'm going to have n factorial. What am I going to have for the others? And here I'm going to have x minus 1, x minus 2, x minus 3, x minus 4. What am I going to have for like some j? Let's see. If I have a j between 1 and n, I'm going to have, so now xi is j. So this is actually, let me just write it out as the product of x minus j over I minus j over this product. For j isn't equal to I, for j isn't equal to I. That's what qi of x is. So now we have this is going to be equal to this, the product x minus j, j not equal to I, j goes from 0 till, what's it called, to n, over the product from j equals 0 till n, and j isn't equal to I. We're going to have what? We're going to have I minus j. And now when you plug in x equals n plus 1, what you are going to need to do is figure this out, which is not going to be beautiful now, is it? So maybe that's a different problem, you know, like how are you going to actually calculate this? Because it's not a simple problem here. How you calculate this is, what do we have? Let's actually try to see like what we have in general. So we're going to have n plus 1 with every single one except, so let me just write this as x minus j, j equals 0 over x minus I. And this, I don't want to write it the same way. I minus j, j minus, I'm inclined to write it the same way on one hand, but maybe not. So let's see what this will be equal to. This is going to be x minus j. So we're going to have p of n plus 1. It's going to be the sum till n for I is equal to 0, 2 to the I. This product is going to be n plus 1 minus 0, n plus 1 minus 1, n plus 1 minus 2, all the way till n plus 1 minus n. So it's going to be n plus 1 factorial over this x minus I. So this is going to be, actually, it's going to be n factorial, because we go from, or no, it's going to be n plus 1 factorial. And then we're going to have n plus 1 minus I. Denominator, and what else do we have here? We have a mess here. And that mess is equal to just something, oh my God, I really would like to avoid this, but it doesn't seem like I can. It's not my day today, it seems. N plus 1, please. So let's see. We have I minus j. So for I is equal to, say, 2, we have 2 minus 0, 2 minus 1, and then 2 minus 3, 2 minus 4, 2 minus... We can have it as j minus I and then get, but that doesn't really help us either. So it seems like it's a mess. And it's now I'm actually starting to question whether or not this is actually possible to calculate nicely. Maybe inductive. I'm not even sure actually inductively. Forget about it. Maybe inductively. So this problem, if you want to go down this route, I invite you to pause for 20 minutes and try to go down this route. And now we're going to do a different type of solution, which has a different type of idea in mind. And here's that idea. So this other solution is one which I actually remember from this problem and why I think the problem is amazing, because you can try to do that sort of difficult calculation, right? And maybe it's not too difficult. Maybe I'm just like a bit untrained or out of training. Maybe I'm like not mathematically fit these days. But let's see. So pi is 2 to the power of I. Let's see a couple of let's say n is equal to 1. What do we have? We have, let's try a couple of n. So a degree 1 polynomial, p of 0 is equal to 1, p of 1 is equal to 2. And we're looking at p of 2, right? So how do we get this? So p of 0 is 1, which means the last coefficient is 1. This means that the second coefficient is also 1, right? So then this is equal to 3. And this is b. For ax plus b, this is b. This gives us b. This gives us the first thing. Okay. Let's look at n equals 2. If p of 0 is 0, p of 1 is 2, and p of 2 is equal to 4. Now if we actually write this down, like how I would actually go about this is a quadratic now. I would write p of x minus 4 is now going to be equal to a polynomial x minus 2 times some linear polynomial, say, L of x. And I know for x equals 1 and 2, like I'm trying to see if I can get it back to, I just need to find a polynomial which satisfies these relationships of a linear type. And is that possible to get? No, maybe pause for 5 minutes and ask yourself that. And here's the solution. And the answer is, well, look, you have this polynomial, let's call this polynomial like this polynomial, let's call it like p of 1, right? p1 of x. Well, if you write p as p1 of x, and then you want to add something to it, right? P of x as p1 of x plus some other polynomial, q of x. You want to have, you're going to have p1 of x is equal to this x for, like q of x is going to be 0 for x is 1 and 2. So you'll have p of x is equal to p1 of x plus, this is actually going to be now x, so for the zeros here are 1 and 2, actually 0 and 1, x times x minus 1. And then because this polynomial is quadratic, and this one is quadratic, right? That means here we only have now a constant term, say alpha. And now p of 2 is 4, that means we have 4 is equal to what we had here, is equal to 3 plus 4 times 3 times alpha. 3 times alpha, which gives us an alpha that is equal to 1 over 12. If I've not made a mistake, that is. And now if the alpha is equal to 1 over 12, what does that tell us about p of other values? Well, it doesn't really help us, or does it? I don't know. This is actually an interesting way to motivate it. I have not thought about motivating it like this. I thought we were going to go another way if we're not motivated like this, but maybe there's a motivation to be found here. Okay, so now we have x times x minus 1 times alpha. We know what alpha is. We know actually this. We know this was equal to x plus 1, right? This was equal to, x plus 1. And now we have x times x minus 1 over alpha. And then that's actually what p of x needs to be, right? There's nothing, we don't actually need to know what this is, but then we know that what this looks like. That's an interesting actually way of looking at the problem. Then this is going to be x squared over 12 minus x over 12 plus x plus 1. Right, it's not looking super pretty once you have it like this. But it's also like asking, but this problem is also asking, like, say we know a couple of these, right? Say we know the n minus 1's polynomial such that p of 0 is 0 all the way till p of n minus 1 of n minus 1 is going to be 2 to the n minus 1. Say we know this polynomial and we're looking at the polynomial for n. And what we would have is this. P of n is going to be equal to Pn of x. It's going to be Pn minus 1 of x plus this q of x, which we know because it's of degree n, and and its roots are 0 through n minus 1. We know it's of this form, this times alpha. And now we can maybe sort of figure out what we're looking at. P of n we figured out here, so we know this value. Like if we're solving the problem in general, that we know this value, that we know what P of n is. It's 1 of n. And we know that this should give us, when we plug in, and here we're going to get 2 of n. And here we're going to get n factorial, right? Actually, n times n minus 1, yeah, n factorial times alpha. Which is why it's a bit strange that I got 12 here. It might have been a miscalculation. I should have gotten a 6 perhaps. But oh no, it's 12 because of the 2 when I divided by 2. So now here, if we know this value, we sort of then will figure out what alpha needs to be. And when we figure out what alpha needs to be, then for n plus 1, we will have what P of n is. Actually, from here, we will be able to figure out what alpha is. And then if we know this polynomial, we know this one. But it's still not very close, right? We still need to get closer to the polynomial. So maybe let's take a step back and ask ourselves, like, how could we maybe construct a polynomial with these things and not explicitly? And here's the big idea, why I love the problem. And this is take 10, 20 minutes and try to push the problem further. Here's the big idea. And the big idea is that, mind you, if you have P of x, you have that, this identity in the back of your mind. N choose 0 plus n choose 1 plus n choose n is equal to 2 to the n, right? So if you construct x as x choose 0 plus x choose 1 plus x choose n, then what you have is, for every, mind you, if x here, if in any one of these, if x is less than the bottom one, say it's x choose k. If x is less than k, then the value is 0. And then you will have the sum from k0 plus k choose 0 plus k choose 1 plus k choose 2 plus all the way till k choose n. And then that sum will be 2 to the k, and then everything else will be 0. So this polynomial, which is a polynomial, right? Everything down here is going to not have x in it. Satisfies this property right here. And given that a polynomial with n plus 1 of these values is uniquely defined, this uniquely defines our polynomial. Could we have guessed that this was in fact a polynomial for n in general, like that this was p n of x. And I think because of this difference, because what is the difference? The difference should be equal to, for x choose 0, so this is for n, the difference is x choose n, right? That's what the difference between these two polynomials is. And x choose n, when we sort of figure out what alpha is, for a couple of these alphas, we can be motivated to actually say, wait a second, this thing here that we're left with is going to be n factorial over, so what do I need? N factorial, x choose n. I need, this is n factorial, but this is going to be x over alpha is maybe going to be n factorial. And, or is it? I don't know, I haven't checked. But this is why I like the problem, why I think it's cool, because now we could have also figured this out via this. And this was to motivate it. And now what is p of n plus 1? Well, it is going to be n plus 1 choose 0 plus all the way till n plus 1 choose n. And to actually solve this, we can use an identity. Actually, wait, let me just double check here. This is going to be, because alpha is going to equal n factorial, 1 over n factorial. That means this is going to be 2 to the n minus 1. So I need to prove that this is 2 to the n minus 1. How do I do this? There's an identity. Oh, we could have actually gone down this route and finished it. I just saw this now. Goes to show like how you can solve problems in many different ways. Oh, cool. So we could have gone down this route. How are we actually just going to solve this? I want to show this also trick. I wanted to also show this trick, which is n plus 1 choose j is equal to. So this is n plus 1 objects. How do I pick j of them? Well, if I pick the first object, then I have, of the n objects, I must pick j minus 1 of them. If I don't pick the first object, of the remaining n object, I must pick j of them. So now we have this equation, and then this we'll be able to write it as a sum of these. So every single one except 0 will come up twice. Then this is going to be, so this is going to be equal to n choose 0. So for 0 is going to be n choose 0 and n choose 1 and n choose minus 1, which is 0. So we're going to have n choose 0 plus n choose 1. So this is going to be n choose 1. Actually, it's going to be n choose 0. Wait a second. So n is going to decrease. N choose 0 is going to come. Oh, n choose 0 is coming twice. N choose 1 is coming twice. So it's 1 from 1, 1 from 0, all the way till n choose n minus 1 is twice. And then n choose n only happens once. Add 1, subtract 1. And then this thing right here is equal to 2 times 2 to the n minus 1. And then this is what Pn of n plus 1 is going to be. I really wish I'd actually gone through with this a bit more. It's a cool problem though. I think it's a very cool problem. Because this idea is like thinking inductively, okay, if I have something for n, can I have it for n plus 1? And it actually seems like I could have easily finished it. Okay. This finishes up the problem. And as always, thanks for problem solving.